Bode plot basics. First, we'll do the transfer function in the frequency domain. This is a low-pass filter. We can see that at node 2, we have a voltage divider and that the impedance of the capacitor decreases with frequency, so V2 must decrease with frequency. And we can write that out in this form. And we notice that tau equals R1 over C1, and this is our final transfer function. And it's true, if we wanted the step function, we would convert Vs to 1 over S in order to get the step function. But this is just a transfer function, and we can think of Vs as just a sinusoid. Now let's look a little bit more about what that transfer function means. S equals j omega equals j 2 pi f, and so f is directly correlated with frequency, and a lot of times we just use S just as a proxy for frequency. All right? And in this case, we have the transfer function, and now we need to look at the magnitude of this transfer function because we have both real and imaginary parts to the function. So the way for this, there isn't the magnitude really. Here is just 1, and we just have the imaginary part squared plus the real part squared, and we take the square root of that. So essentially the magnitude becomes 2 pi f squared plus 1 over tau squared times 1 over tau. And just keeping in mind that when we say the imaginary part, we strip out the j, because of course j times j equals minus 1, but like I said, this is just the magnitude, so we just take the imaginary part and we ignore the j. Now we do have some regions of interest. One where the frequency or the imaginary component is a lot less than the real. One where they're equal, and one where the frequency component is a lot greater than the real component. And so in these three cases, you can go through the columns in the notes, and you can see that when f is a lot less than 2 pi over tau, which happens to be the cutoff frequency, the magnitude is 1 over the square root of 1 over tau squared times 1 over tau equals 1. When we're equal to the cutoff frequency, the magnitude is 1 over the square root of 2. And when the frequency is much greater than the cutoff frequency, the magnitude is 1 over 2 pi f tau, which is, add all this together, and that will be the complete response, and that'd be a low pass. Now we can use the Excel to calculate the frequency response. And I have a column of resistor, capacitor, tau, calculated from RNC. I have a logarithmic progression of frequency. I calculate the imaginary part, the real part, and then I calculate the magnitude, and then I calculate it in dB. So if we look here with frequency at about almost around 15 gigahertz, we can see that the magnitude is 0.707, which is 1 over the square root of 2. And on the 3 dB scale, or on the dB scale, excuse me, minus 3 dB point is read at about 15 hertz as well, 15.9 to be exact. Now you can also do this actually more easily in LT Spice with an AC analysis, and In LT-Spice, you just have .ac deck. Use a step the response by decades with 10 points per decade from 1 hertz to 100 kilohertz. You can always download this file on LT-Spice, and when you run it and we measure the 3 dB point, minus 3 dB point, excuse me, it's 15.9 hertz. We always use an AC input magnitude of 1 volt because V out then V in just becomes V out in dB, and you don't actually have to type in an equation to do it. Now let's look at the high pass filter. We've just swapped these. It's a voltage divider again, except now the impedance of C1 still gets smaller with frequency. That means with frequency V2 rises. And we can see that in the derivation of the transfer function. Now we have an imaginary part on top, but with nothing real to add it in the magnitude, it's just 2 pi f. And on the lower half we have 2 pi f squared plus 1 over pi, 1 over tau squared. So we still want to look at when the frequency component is a lot less than 1 over tau, when it's equal to 1 over tau, and when it's much, much greater than tau. Again, we have the 3 cases. The cutoff frequency is the same. It's just the frequency response is going in a different way. So when the frequency is a lot less than the cutoff frequency, the magnitude is 2 pi f tau, meaning it's increasing with frequency. When they're equal to each other, we get the magnitude of 1 over the square root of 2, or in dB scale, that's minus 3 dB. And at high frequencies, these cancel out and we get 1. You can again run this in LT-Spice, and you can measure the 3D point at 15.9 hertz. Now, another thing is that active filters can buffer these RC filters. And so if I put in a non-inverting op-amp, which we can by inspection see, you get a gain of 2. So we just multiply 2 times the original transfer function, and here's an equation for the bode plot. And so now the gain is 6 dB, and the minus 3D point will still be at 15, except it won't be minus 3 dB down here. It's measured from the highest point, which is, this case, 6 dB.